At the beginning of this presentation, we start working in an ErlangPro developer or builder environment. System-wise, this is a Linux shell where all tools required to generate the target image are installed. Our first task is to build a target ErlangPro image with a vendor application installed in it. Here are the resources required to do it. We can see a generator script, generate.sh. There is a file that contains a list of repositories to take the basic target contents from. There is also a list of additional packages to install into the target image. This is a basic set of convenient Linux utilities. The last file to take note of is a Unix archive of the vendor software application. It has been modified to contain scripts required for its correct installation. This will start the generation, which then goes on for a few minutes. We can see how the resources are being imported from the repositories and how the packages are being installed. The image has been generated. It includes an operating system kernel and a bootable RAM disk with the requested applications installed. This image can be copied to whatever location should be used for booting up. We will make several copies, 3 according to the number of Erlang nodes in our demonstration, and move them to locations from where they will start. Now we are starting a head node using a specialized script, similar to one that starts a worker node. However, it includes additional options for configuring the kernel. We have started the head node and it is running now. We are logging in as an administrator with an access key and see a command line console interface which suggests a native ErlangPro specific set of commands. Using one of the available commands, we can see what system applications are running on the head node. There are several monitoring applications, a CLI server, a user authentication service, etc. Next, we are going to start 2 more nodes of our distributed system, those to be worker nodes. We can see from the output of the application listing command that there are 3 nodes running in total. Each node hosts a node agent that provides collection of monitoring data and connectivity to the head node. These 3 nodes are not yet of much use because they have no file system to work with. We can see it through an appropriate command. So let's add one. To add a file system, we type a command, a file system type, and URL of a mount point exported earlier from an appropriate host. Now all 3 nodes have the file system mounted and ready to use. More mount points can be added if needed. The next step is to get the nodes ready for running Riak. We perform some configuring by setting global parameters of this application for all the Erlang nodes currently running. We can see the configuration parameter added to the system, which provides connectivity of the distributed application on the nodes. It is time to launch an instance of the Riak server. Let the host for it be second worker node. Okay, we can see the instance is working. We follow by launching 2 more instances, one of them on the head node. By the way, nothing can be launched on the head node other than forcedly, using an appropriate option. Let's do some testing on the active Erlang nodes. In the production environment, there will be no need to log in onto particular worker nodes. All of them will be reachable through the interface of the head node. But now we have logged in on node 2 and can see a list of processes currently running on it. Let's take a look at the list of all React nodes and the configuration of the React cluster currently running. Next, we can see the status of the React cluster. Now, we run a React read-write test and see it complete successfully. The same can be done on any node where this distributed system is running. Now the uptime of one React node. We can reboot any worker node through the command console of the head. And make sure the reboot has worked by looking again at the uptime. Now the uptime. We can see the status of the distributed vendor application on all nodes and ensure its connectivity. The application reports that all nodes are reachable. Now we shut down and start the whole cluster up again. Now we start the whole cluster up again. The launch sequence is not really important because the worker nodes will wait for their head to start up. Now we can see that the reboot restores the system to its last configuration. With the system applications working properly on the nodes, the file systems properly mounted, and the distributed application in full connectivity and operability. Let's make sure all nodes are under monitoring. Now we can see a long list of sensors available on a node, all accessible through CLI. Various filters can be applied to the monitored data, and an administrator can access any information of interest. For example, let's see a CPU usage across the whole cluster of nodes. Let's imagine we have to add another node to a working cluster. First, we start the node itself. And then launch one more instance of Riak on it. Next, we log in. Next, we log in on that node and run the React tests. push to. We can see everything works okay.